Hello, this is me going through some photoelectric effect exam questions. The link to where they will be in the video, in the description. It's from Physics and Maths Tutor. I'm not going to go through the theory here because I've done a 35-minute video going through all of that, so you can use that yourself to see what's going on. But I will go through the answers to this. So I would recommend pressing pause, doing one question, pressing play and watching me go through it, then pressing pause, doing the next question, and so on. Okie doke, so we're going to start off with the following equation describes the release of electrons from a metal surface illuminated by electromagnetic radiation. Explain briefly what you understand by each of the terms in the equation. Okay, so HF is the energy of the photon, or a photon. KE max is the KE of the emitted electron, or photoelectron you can call it. I should probably say that it's the maximum KE of the photoelectron, but that isn't actually on the mark scheme. And phi is called the work function. And what is meant by that? It's the energy needed to release an electron from the surface of a metal. And hopefully you can read that. Looks like you can. Next up, calculate the momentum P of an electron travelling in a vacuum at 5% the speed of light. Now this is a bit of a switch away from the photoelectric effect, but let's do it anyway. This is mechanics, P equals mv. And you're given the mass of an electron in your formula sheet. It's 9.11 times 10 to the minus 31 kilograms. And then we're looking at 5% the speed of light. So I'm going to do 0.05 times 3 times 10 to the 8 meters per second. I'm going to find my calculator. Hopefully you can see it in shot there. So 9.11 times 10 to the minus 31 times 0.05 times 3 times 10 to the... It's annoying, isn't it? 9.11. I have got the mark scheme here, but I think it's useful to actually do the sum. There we go. And I'm getting the right answer, which is good. 1.37 times 10 to the minus 23. And it's a momentum, so there's different ways I could write the unit. I'm going to write MV, kilogram meters per second. You can also write Newton seconds if you want to. Okay, so what is the de Broglie wavelength of electrons travelling at this speed? So de Broglie wavelength, lambda equals mv over h, or momentum over h. And we've just worked out momentum, so we're going to use the same number, 1.37 times 10 to the minus 23. Hang on, I'm very sorry. Lambda equals h over p, not mv over h. Equals h over mv. So it's going to equal h, which is 6.63, that's Planck's constant, times 10 to the 34, divided by 1.37 times 10 to the minus 23. It's been a long time since I taught the de Broglie wavelength. It's on the other side of the course to me. So 6.63 times 10 to the 34, divided by the answer, and I get lambda equals 4.8. Oh, this seems wrong, doesn't it? What have I done there? This is minus 34, that's why. 6.63 times 10, I'm not doing very well, it's very light, times 10 to the 34, divided by 1.37 times 10 to the minus 23, that's better. And I get 4.8 times 10 to the minus 11 meters. Before I had 52, I don't know if you saw it, 10 to 52, which is far too large. So yeah, it should be very, very small. And it says, why are electrons of this wavelength useful for studying the structure of molecules? Well, we get most diffraction occurs, as in like the maximum diffraction occurs, when the wavelength equals the gap size. So remember, diffraction is when waves pass through a gap and they spread out like this. Here, studying the structure of molecules, the de Broglie wavelength of the electrons is similar to the spacing between atoms. So we're going to get most diffraction, and we use those interference patterns to then work out what these molecules look like. For example, X-ray crystallography uses a similar thing for that. Okay, so that the very first part of that was about the photoelectric effect. The rest was a bit more about wave-particle duality, but not bad to look at anyway. So press pause if you need to do question 2. I'm going to do a bit of a shuffle so you can see both parts of the question at the same time through the magic of cameras. I'm sorry it's quite dark, but it is at night because I haven't got time to do this in the day. So there's the 2 questions if you need them. Press pause, have a go at them, and then we'll go through them. Okay, I'm going to go back to here because it's much easier to do it when they're not all funnily put. Okay, so the graph shows how the maximum KE T, and they've called it T for some reason, of photoelectrons emitted from the surface of sodium metal varies the frequency F of the incident radiation. So if you were watching my previous video, you'll notice this looks very, very similar, if not the same, to this graph here. So we might use that in a moment. So firstly, why are no photoelectrons emitted at frequencies below 4.4 times 10 to the 14 hertz? Well, this must... Have I missed something out? No, I think that's a later question. Oh, sorry, that's a later question. I was looking at the mark scheme and something extra seemed to be in there. Okay, well, this here, 4.4 times 10 to the 14 hertz, is the threshold frequency. And what we can say is that below this frequency, the photons have too little energy to emit electrons, because what we'd find is that the photon energy would be smaller than phi, which is the work function. And then we're told to calculate the work function phi of sodium in EV, and that's electron volts. Now phi is equal to HF0, where F0 is the threshold frequency. If that's something you're not sure about, have a look at that other video that I've made. So if we're going to use that, I'm going to say that it is equal to 6.63 times 10 to the minus 34, and then multiply that by F0, which if I try and read off, if this is 8, that means that is 6. So this must be 5 there. So this is about 4.4. 4.4, oh, hang on. I don't know why I read all that off because it's just told me there, hasn't it? So 4.4 times 10 to the 14. Good bit of graph skills at least. And if I do that sum, hopefully you can see, there we go. My light isn't showing up very well today. 6.63 times 10 to the minus 34 times by 4.4 times 10 to the 14. I get that phi equals 2.9172 times 10 to the minus 19 joules. But to get that into electron volts, what I'm going to have to do is divide that by 1.6 times 10 to the minus 19, which is the charge in an electron. So divide by 1.6 times 10 to the minus 19, and I get an answer of 1.8 electron volts, which is the correct answer. Okay, explain how the graph, which I might keep, I'll put it over on the side. Explain how the graph supports the photoelectric effect HF equals T plus phi. So we've talked about this in terms of how we rearrange the equation y equals mx plus c to match up with this equation here. This one's probably better up there actually. And we basically need to explain that in words, okay? So I'm going to say compare to y equals mx plus c, where t is y and f is x. So let's kind of write that out. So I can write y equals mx plus c, and that's going to be the same as t equals hf minus phi, because if I want to have phi on its own, I need to move it over. So there's a couple of things I can say. I can do this, and I can say, therefore, negative intercept shows, yeah. The y-intercept equals minus phi, or I could say that the gradient equals Planck's constant. And as it's a constant, I therefore get a straight line graph because y equals mx plus c with m as a constant is the equation of a straight line, which supports this as well. The mark scheme is not particularly lovely here. It says t equals hf minus phi similar to y equals mx plus c, yes. Straight line shows t/f relationship, so the fact that they are, as you increase one, you increase the other, they're linear. And the negative intercept t-axis shows phi. I think what I've written is better personally, but there we are. Now, how could the graph be used to find the value of the Planck constant? Nice and simple. I've already shown it up here. I've said the gradient equals h. So from the gradient is absolutely fine. Now, what you don't need to mention, but what you would need to do, would be to convert, because your kinetic energy is in electron volts. You'd need to have it in joules for it to be the Planck's constant, but you don't have to say that. And then finally, we've got add a line to the graph to show the maximum Ke of the photon electrons emitted from a metal which has a greater work function than sodium. If it has a greater work function, if I draw this graph as I would if I had like the whole of the axis, okay, the current graph would look like this, okay. If I had a greater work function, remember the y-intercept equals minus phi, a bigger work function would therefore be more minus. So this would be a greater work function. So the graph would look like this. So on this one, I'm going to draw in a line like that. And it also works because a greater work function would have a higher threshold frequency. So your x-intercept should be further over. So that's question 2. Now we get to some proper questions, I find. Written questions are good for the photoelectric effect. So question 3, experiments on the photoelectric effect show that the kinetic energy of photoelectrons released depends on the frequency of the incident light and not its intensity, and light below a certain threshold frequency cannot release photoelectrons. How do these conclusions support a particle theory but not a wave theory of light? And it's a 6 marker with very little space. Have a go. There are some really common things you have to say for these questions, but see what you can do. Press pause and then press play when you're ready to talk about it. Okay, we're going to talk about the stuff that you always have to write in a photoelectric effect question. Firstly, we say that the particle theory states light can act as particles called photons, which are energy packets or quanta, and I'm going to say called photons with energy that is proportional to frequency, because E equals HF. This is something to always say. A photon has an energy E equals HF, and you want some idea that photons are packets of energy, that energy is proportional to frequency, or that E equals HF. The other thing to always say is one photon can interact with one electron only. This one-to-one interaction is important, giving the electron all of its energy. No more, no less. Okay. Now, photoelectrons can only be released if the photon absorbed has a high enough energy, i.e. HF, the energy of the photon, has to be bigger than phi, which is the work function. Important, I've talked about energy here. HF is an energy, phi is an energy. You can also say, or it needs to have a high enough, I'm going to use a different colour pen, a high enough frequency, i.e. F is bigger than f0, which is the threshold frequency. Okay. Now what we find is that increasing the frequency of light increases the max Ke of the electrons, but not the number of electrons emitted per second. This would not be the case with the wave version of light, okay? So I'm going to write that down. This would not be the case for the wave theory, if it supported the wave theory. We also find that increasing intensity only increases the number of photoelectrons emitted per second. And for the wave theory, increasing intensity would allow any frequency. Let me just check this on the page. Light to emit photoelectrons, and this is not seen. Okay, so if I show you the mark scheme for this, once again, not lovely, but here we are. So we've got particle theory, E equals HF, or implied packets or photons. One photon releases one electron, giving it Ke, and I've talked about there, so one photon can interact with one electron only. I've talked about the maximum Ke here. Increase F, greater Ke of electrons. Increasing frequency of light increases max Ke. Energy depends on intensity or amplitude. This is for the wave version. More intense light give greater Ke, not seen. So for the wave version, more intense light would give a greater Ke, we don't see that. More intense light would give more electrons, but no change in maximum Ke, that's what we see. Waves, if the waves are continuous, when enough are absorbed, electrons should be released, not seen. Not a very nice mark scheme, but we've answered all that in that little bit there. I think I've written it better once again than the mark scheme personally. So then we've got calculate the threshold frequency for a metal surface which has a work function of 6.2 electron volts. So we're going to go back to work function equals HF0. So F0 is going to equal the work function divided by H, but we do need to have that work function in joules. So it's going to be 6.2 times 1.6 times 10 to the minus 19 to get it into joules, and then divide that by Planck's constant, which is 6.63 times 10 to the 6.63 times 10 to the minus 34. Let me just check that one. Yeah, that is right. There's lots of constants that are all very similar, and that is one of them. So 6.2 times 1.6 times 10 to the minus 19 divided by 6.63 times 10 to the minus 34, and we get hopefully the right answer. No, that seems odd. What have I done there? This was going to be strange, wasn't it? Once again, let's try that again. 6.2 times 1.6 times 10 to the minus 19. Oh, it's wavelength, that's why. Divide that by 6.63 times 10 to the minus 34, and I get that the threshold frequency is 1.496 times 10 to the 15, but threshold wavelength, not something we've come across before, but it's going to be the associated wavelength of that frequency, and we're going to use the equation C equals F lambda for that. So lambda equals C over F equals the speed of light, because this is light we're talking about, divided by that threshold frequency, 1.496 times 10 to the 15. So 3 times 10 to the 8 divided by that answer comes out as, phew, there we go, equals 2 times 10 to the minus 7 meters, which is the answer. I had a small panic there. And to which part of the EM spectrum does this wavelength belong? This is something that you don't really need to know anymore, but just to let you know. This is UV. If you think about, so light would be about 700 nanometers, which is about 7 times 10 to the minus 7 meters. So if you're getting smaller than that, you're going to go towards UV. And if you're not sure, the photoelectric effect generally works with UV and not other lights. Right, carrying on. There's only another many more to go. What are we on? Only, 5 more to go. So question 4, the diagram shows monochromatic light falling on a photocell. As the reverse potential difference between the anode and the cathode is increased, the current measured by the microammeter decreases. When the potential difference reaches a value Vs, called the stopping potential, the current is 0. Explain these observations. This is all about the photocell, which I did talk about in the other video. I would recommend potentially watching that if you aren't really sure what's going on here, because it is quite tricky. I'm going to do this on a separate piece of paper because I'm going to definitely run out of space. So let's do it like this. There we go. So press pause if you need to, and then have a go, and then come back to it when you're ready to go through the answer. Right, this is trying to explain one of the hardest things in A-level physics in a nice 6-mark question way. So let's think of what's happening. Now the photocathode, or the photocell, on that we can say that electrons are released when photons are incident on it. So when there are incident monochromatic radiation onto the photocathode, they're released, and then these electrons have a Ke and travel to the positive anode, because anodes are positive. Okay. Now, what we know is for this to happen, the photon energy, HF, must be bigger than the work function phi. Obviously, you need to write this in proper English. And we can also say one photon interacts with one electron. Hopefully you're seeing a bit of a pattern here. This is very, very similar to what I wrote here. Okay, so for this to happen, photon energy has to be more than the work function, and also one photon will interact with one electron. Now, these electrons are released with a range of kinetic energies. And that's because we talked about this in the other video. So if you need to look back, I'm just trying to find my little picture. The work function is the energy needed for the electron to escape the surface of the metal. But if an electron is coming from deeper down in the metal, some of that spare energy is going to go into getting them to the surface before they escape. So you're going to get a range of energies. Now, the stopping potential opposes this and slows the photoelectrons down as it does work on them. And that work, W, equals QV, where I could also write equals EVS. E is the charge on an electron, Vs is the stopping potential, or what will eventually become the stopping potential. As V is increased, more work is done against the electrons decreasing their Ke and slowing them down. Slow electrons mean a lower current, and so a lower reading on the ammeter. Okay. Eventually, when V equals Vs, the stopping potential, the electrons are stopped completely. And the current equals 0. Apologies for my handwriting getting worse and worse there. But that's my written explanation for how does the photocell work, which is one of my least favourite questions, I'm not going to lie. So now we're going to probably need to use that picture in a moment, so I'll bring it back in a second. Have a think about this next little bit of the question, which is here. What would be the effect of the stopping potential of increasing only the intensity of the incident radiation and increasing only the frequency of the incident radiation? So this is trying to get you to work out which one of these things is going to change the Ke max. The stopping potential works against the maximum Ke. Which one of these is going to increase the Ke? Well, if you remember the equation, HF equals phi plus Ke max. If I want to increase the maximum Ke, I either need to decrease the work function. H is a constant, so I can't change that, or I need to increase the frequency. So if I increase the frequency of the incident radiation, the Ke max will increase and therefore the stopping potential will increase. However, increasing the intensity of the incident radiation is not in that equation, so that will have no effect. Right, carrying on. Question 5. Hopefully you can see it. Press pause, have a go, see what you can do, and then press play when you're ready to carry on. Okay, experiments on the photoelectric effect show that the kinetic energy of photoelectrons released depends on the frequency of incident light. Light below a certain frequency cannot release photoelectrons. How do these conclusions support a particle theory but not a wave theory of light? You may be awarded a mark for the clarity of your answers. I'm going to be really lazy here and just show you the mark scheme and talk about it because I can't bear to go through all this again. But really good practice for you. Look what the mark scheme looks like. One photon releases one electron, giving it Ke. That's the same as what we had before. If you increase the frequency, you have a greater Ke of electrons, the same as that we had before. Lower F, you eventually get to no Ke, as in there are no electrons released. That's in particle theory. Okay, that's really similar to, I'll put it down somewhere. So, it's on the same page, that's why. Have a look, that's really similar to the one up here. Particle theory, E equals HF, implied packets of photons. One photon releases one electron, giving it Ke. Increase F, greater Ke of electrons. Lower F, finally Ke equals 0. So this whole section here completely correlates with this section here. They ask the same thing about this and expect the same thing over and over again. But if it was the wave model, more intense light should give a greater Ke. More intense light would give more electrons, but no change in maximum kinetic energy. So this one here, if it was waves, this is what would happen. What actually happens is this. These mark schemes are not very clear. More intense light gives more electrons, but no change in maximum Ke. Look at the same thing here. So this bit, I'll do it in pink, matches up with this bit here completely. Okay, so if you're looking at the marks, you can see it a bit better. If waves are continuous, when enough are absorbed, electrons should be released. If waves are continuous, when enough are absorbed, electrons could be released. So let's add all that together. It's the same mark scheme. I think word for word. They just haven't got this particle theory, E equals HF, implied packets or photons. So we can use the same answer as before, essentially. This one here. So feel free if you want to go back and look at that again. But the question comes up over and over again. So question 3 and question 5 are very, very similar. And I'm being lazy and not going through it with you. But I will go through the next part, which is a bit different. Oh no, it's once again basically the same question as the other one. The graph shows how the kinetic energy K of the emitted photoelectrons from one metal varies with the frequency F of incident light. Add a second line to the graph showing how K will vary for F with the second metal that has a smaller work function. Now before, there's so many pieces of paper going around, which are all the same as each other, that I'm getting lost. Before, in this question, we were asked to draw a line for a higher work function. For a lower work function, we want the line to intercept the y-axis higher up, closer to 0. It's going to look like that. So instead, we're going to draw a line here. Right. question 6. I'm going to show you both parts at once so you can have a go at it. So hopefully you can see all of question 6 there if you're just pausing the video and doing it that way. Otherwise, you know, hopefully you're doing it from the PDF. Have a go and then press play when you're ready to carry on. Okay, question 6. The diagram shows monochromatic light falling on a photocell connected to a circuit. So it's very similar to the last question we did, but this time we're going to use some maths. The incident radiation has a wavelength of 215 millimeters. The metal surface of the photocathode has a work function of 2.26 eV. Calculate the energy in eV of a photon of the incident radiation. So incident radiation E is equal to HF, but I've not been given frequency. However, what I can say is that C equals F lambda, so F equals C over lambda, and I can write this as HC over lambda, which is quite a common equation. The energy of the photon in terms of wavelength is HC over lambda. So energy equals 6.63 times 10 to the minus 34 times the speed of light, 3 times 10 to the 8, divided by 215 millimeters. So 215 times 10 to the minus 3. Put those numbers in. Times 3 times 10 to the 8, divided by 215 times 10 to the minus 3. And I get an answer. That feels wrong. Instant radiation. So E equals HC over lambda is the right value. You can tell it's really late. 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by 215 times 10 to the minus 3 equals that. I'm going to go with the flow. 9.2511 times 10 to the minus 25. And then I need to turn that into an electron volt. So I'm going to divide it by 1.6 times 10 to the minus 19, which is where... And I get, yeah, I think I know what's wrong here. So 5.78 times 10 to the minus 6 eV. So I seem to be out. Yes. So a wavelength of light of this is what freaked me out to start with. A wavelength of light of 215 millimeters is horrifically high. So really, this should be nanometers. And if this is nanometers, this will be 10 to the minus 6 smaller. So I'll get 5.78 electron volts. There we are. This is why you should do the questions before you do your video. But that would imply lots of time. So I've got 5.78 eV, which is the right answer. Then what is the maximum kinetic energy in eV of the emitted electrons? Well, I'm going to use, here we go, the metal surface of the photocathode has a work function of 2.26 eV. We're going to use the equation E equals HF equals phi plus KE max. So KE max is going to equal HF minus phi, which is 5.78, that was HF, minus the work function 2.26. And 5.78 minus 2.26 comes out as 3.52 electron volts. And then it says, write down the value of the stopping potential. If you ever get something that just says, write down, because this is in electron volts, that means the stopping potential is the same value, but in volts, 3.52 volts. And that's to do with the fact that KE max equals the work done, which is equal to QV. But Q is in electron charge and volts is here. So if I have this in electron volts, I can just say it's the same in volts for the stopping potential. And the write down bit is the kind of the hint there. So if the wavelength and intensity of the incident radiation is kept constant, a graph of the current through the photocell applied against applied PdV is shown. It's this beautiful shape there. Let's put one of these together. Mark a letter S on the graph to show the stopping potential. Now the stopping potential is going to happen where the current is 0. So the stopping potential is going to be here. Then the photocathode is replaced when, when the current is 0. Yeah, that's right. The photocathode is replaced with one whose metal surface has a greater work function. On the graph above, so this graph here, sketch how I would vary with V, given that the wavelength and intensity of the radiation remain unchanged. So I'm going to think about the equation HF equals phi plus KE max, but instead of KE max, I'm going to write plus EV, because EV and KE max, they equal each other over here. So they're asking me, on the graph above, sketch how I would vary with V, given that the wavelength and the intensity of the incident radiation stay the same. So F is staying the same. H is going to stay the same because it's a constant. I'm told that the work function is increased, but electron charge is going to stay the same. So if the work function is increased, that means that the stopping potential for HF to be constant must decrease. So I'm going to have a smaller stopping potential. So it's going to have to start, the smaller stopping potential is going to have to start here. I am told that F stays the same and intensity stays the same. So I'll eventually get to the same level of current, but it's just going to take longer. So it's going to look something like this. It's going to be the stopping potential that is smaller. Not a very nice question, but that's the point of this, is to try and do some difficult questions. Right, nearly there. I am quite tired. It is now nearly 9 o'clock. So mark question 7. Have a read through and have a go. It's another written one, but it's quite a short written one. Okie doke. The photoelectric effect supports particle theory of light, but not a wave theory. Below are 2 features of the photoelectric effect. For each feature explains why it supports the particle theory and not the wave theory. So the emission of photoelectrons from a metal surface can take place instantaneously. Now the particle theory for this is that one photon interacts with one electron, and I'm going to write in brackets instantly. All the photons' energy is transferred at once, but in the wave version, energy can be built up over time. Therefore, we get a time delay between turning the light on and the electrons being emitted, whereas that's not what happens in real life. And then instant light with a frequency below a certain threshold frequency cannot release electrons from a metal surface. Explain. Well, for the particle theory, that tells us that the frequency, a smaller frequency, means a smaller photon energy. E equals HF. If this energy is smaller than the work function, the electron can't escape. Okay, but in wave theory, we would find that any frequency could emit electrons if given long enough, because we have this building up idea. It's going to take longer. Okie doke, final question. We are on 38 minutes. It's quite a lot. Question 8. The graph shows how the maximum kinetic energy T, once again, why it's T, who knows, emitted from the surface of a sodium metal varies with the frequency F of the incident EM radiation. Have a read of the question, have a go if you need to press pause and do it. Otherwise, I'm going to talk about it. Use the graph to find a value for the Planck constant. Now, we know back from many times that we've tried this. I'm going to go back to my little piece of paper that's got it on for my other video. We know from here that if we have a graph of Ke max versus frequency, the Planck constant is m, the work function is the negative gradient. So to find the Planck constant, we're going to work out the gradient of the graph. And to do that, I need to actually do a gradient. I'm going to just choose the points that seem easiest. So I'm going to go here, which is 56. Hang on. So it's a change in y over the change in x. The change in y, let's go from, this bit looks all right. That is 4.2 minus here is 0 times 10 to the minus 19. You might have different values, divided by the change in x, which is 12 minus 6 times 10 to the 14. Be careful of those little 10 to this there. I'll get my calculator out. 4.2 times 10 to the minus 19 divided by 12 minus 6 is 6. 6 times 10 to the 14. I get the gradient equals 7 times 10 to the minus 34, which is about right because we know it's 6.64 times 10 to the minus 34, and it should be joule seconds is the unit. In the mark scheme, you're allowed between 6.3 and 6.9. My excuse is this is very, very small, so I'm slightly out because it's harder when things are smaller. Use the graph to find the work function phi of the sodium metal. Well, if we go back, phi is the negative y-intercept. So I would take my pen, not my pen, I would take my ruler, just desperately trying to find it. I would draw and I would extrapolate this line, which is why they've done this for, until it hits there. And I find that this is about, I've got this is about minus 3.5 times 10 to the minus 19 joules, but it's minus that 3.5 times 10 to the 19 joules, and you get your answer there. And finally, calculate the stopping potential when the frequency of the incident radiation is 9 times 10 to the 14 hertz. Now, we've got the equation HF equals phi plus KE max. But remember, stopping potential, we can also say HF equals phi plus EVS, where VS is a stopping potential. So we want to know VS, that's going to equal HF minus phi, all divided by E. H is 6.63 times 10 to the minus 34. The frequency, I'm told, is 9 times 10 to the 14. The work function I've worked out is 3.5 times 10 to the minus 19, or whatever you got for that, and divide that by the charge in an electron, 1.6 times 10 to the minus 19. So 6.63 times 10 to the minus 34 times 9 times 10 to the 14 minus 3.5 times 10 to the minus 19 divided by the charge on an electron. And we get an answer which seems quite sensible, of 1.54 volts. So it depends on you might get something slightly different there because it depends on your value of the work function, but you're allowed between 1.1 and 1.8 volts. So that is perfectly fine. So I should learn my lesson about doing these videos late at night when I'm tired and had a full day of teaching and I haven't had time to properly prepare them, but I figure it's better to have something rather than nothing. So hopefully that was useful, and hopefully you've seen how the questions do generally seem to follow similar patterns. They like the same things over and over again, talking about one-on-one interaction, talking about the threshold frequency or the work function, using this lovely equation, knowing about the stopping potential, using this graph, knowing how to use it. And hopefully that was helpful for you.